Okay, welcome back. We're still talking about CNC systems, and we have three parts that we'll be covering. So the first one is the axis drives. So building on this chapter's explanation of the kinds of axis moves a CNC machine can make, and we saw some examples with my introduction. Now we can look at, quote, how they make these moves. How do CNC machines make near perfect surfaces while cutting into and out of changing material loads? Kind of cool that that's possible. And even with varying excess from one part to the next and cutters doling, they still deliver clone parts each and every time within the allowed tolerance that the machine can actually perform at. So that's what we see. So we're now just getting a little bit of a thought here in terms of the this first part here with let me go back, thinking about the axis drives. So there's 5 components. Compare the ways a CNC axis moves to lifting a load with your arm. So we have a picture there you can see. So following a program that the central controller sends a low energy signal to relays the same way the signal goes to your muscle synapses. Next, the relays amplify the signal to drive the individual axis motor. So that's muscles and tendons all working together. So in terms of some shop talk related to this, so the controller doesn't drive the motors. It sends commands to sophisticated relays that process the low energy signals into custom high energy commands that drive the individual axis motors on the machine. That's why a single controller can run any machine, big or small. Relays do the translating. So we're getting a little bit more details of the function with that kind of a description. So for the kinetic sense, the feedback signal, okay, the signal's made to the arm muscles and it's moving to the load, or isn't it? The motors turn translation screws so the X, Y, and Z begin to move at the rate the controller commands. As they turn, sensors on the screw or on the axis itself begin sending a signal back to the branch to let you know how things are going. Your arm too. Using a clock function, the brain compares real-time progress to command expectations. So thinking again in terms of shop top, the entire set of interconnected components is called a closed loop linear servo drive system. But we can shorten this to something easier to think about, is just think of it as a drive system. So there's all kinds of calculations that are going on, calculations like crazy. The central processing unit is not only interpolating various feed rates and switching things on and off, it's also comparing progress achieved to the time factor for expected progress and then deciding what to do about it. So it's trying to keep on schedule, if you will, some, but not all CM machines can push even harder if they lag behind. Most controls just accept a tolerance for lag. When an axis drive goes lag, small shape errors can occur. If they go behind preset limits, the machine shuts down and shows a servo error. So having feedback is a useful thing to have or not to have. And so consider that point of view. Most CNC machines feature closed loop feedback system, but a few are made without it. This is not a good thing in terms of accuracy, but it saves lots of costs without sensors or higher level CPUs. And so that can be one of the trades that might have to be made for what you need and what the tolerances you have for inaccuracies. For light duty machines like wood routers, for example, an open loop machine is, quote, okay. Lagging isn't a problem, but feedback is essential on industrial lathes and mills. So a little bit more on open loop machines. You could clamp the table in place on an open loop mill, then run a program. Oblivious to the problem, the controller would happily continue sending out commands, never realizing nothing is happening other than the heat in the motors. It has no sense of how things are going at the drives. And so that's the liability you would have. So for ball screws, in an earlier chapter in the overall textbook, we're not going to be talking about this, but this is just giving a reference if you wanted to get the whole textbook discussed in chapter 13. At the absolute heart of most CNC machines are the ball screw drives. They make it possible to mill complete circles with no backlash appearing as each axis reverses while the cutter is in contact with the work. No manual machine with Acme drive screws running adjusted split nuts could do that. We're talking zero backlash. The ball screws are driven by highly controllable electric motors called servo motors. They rotate a predictable exact amount when given a specific amount of input energy. So this is just an illustration of a recirculating ball screw, the outer channel feeding the ball bearing back to the far end of the nut for long movements. So we have that. So a second kind of drive motor is a linear drive, envisioning a linear drive to be a rotary motor, but unwound into a flat set of magnets, requiring lots of energy to move a CNC axis and also hold it in place during machining. Linear drives are less popular, but they are fast. And so you can be thinking about those trades in case you experience that. Okay, I'll pause and I'll come back to doing the second of 3 sections for this part of our module.